right? So this is a very costly thing. And then development time is short. Yeah, the NVIDIA has already made it for you, developed it for you. So you just need a software to put on it and you can run on it. FPGA is a moderate one. I would tell you how, because we are having very good tools of FPGA modeling, so we can make it easily. And then S6, you have a long time. As I would just tell you in some time how is it long. Then if you are designing ML accelerator, so you should be knowing how actually the accelerator is designed. So I would discuss with you the first one, in which, as you remember some previous slides that we saw CNN, in which there was an input. Input was the image, and what we were multiplying with that to get the features extracted, we were multiplying kernel with the inputs. So those kernel is basically the weight, right? The weight, and the input is the input value. So the pixels input value would be a floating point number, and kernel would also be a floating point number. So we need to store them at any place on the chip, right? Because we need to multiply them. So over here in this, you can see that this is a multi-band input buffer in which we have kept the pixels of the image. Imagine CNN performing through this accelerator. So in this multi-band input buffer, we have put the inputs of the image, and then in DRAM, this is dynamic random access memory. So this gets on when you switch the power on of the circuit. So in this DRAM, what you're doing, you have kept the filter coefficients, the weights. So what you do, there's a top level controller. So why the software is there, we would discuss later, but there's a top level controller that controls everything through the software. So this goes and this gets shared, and then you see that there's a network on chip that shares the data also. And then what happens is, from here the input goes through this arrow, and from DRAM there is a buffer that stores the weights, and then weights and inputs both go together and get multiplied in the PE array. Why we need multiplication? As I told you in the previous slide, that convolution requires multiplication and addition. So in this PE array, you got this multiplied, right? The weights and the buffers. All right. So when the weights and buffers, now this PE array is not one, they are parallel PE arrays, many hundreds. And then it depends on number of neurons that you need to multiply. So when these PE arrays get multiplied, the data is shared to the software and you get the outputs. So this is how the CNN accelerator of Microsoft works. Similar to this is another architecture. Now you consider this thing that each and every year there are hundreds of ML accelerators proposed in IEEE conferences, IEEE journals. So I've just discussed two of them, and there are very good and very efficient circuits presently available. So I have just discussed the ones that would be easy to understand. So here also you can see that they have used data router, that these buffers contain the input data which was stored here. The pixel images, image pixels, these are stored in buffer, and then they go to the data router, and then they go to MAC. As I told you, that multiplication and accumulation would be taking place. Here you have the weight buffer, and somewhere here would be memory, which they did not show in the diagram. So this weight buffer provides the weight, and this weight and inputs, they get multiplied, and then with the marks they get selected, and then you have biases. If you know in neural networks, you would be knowing what is a bias. The bias is added to get more efficient output, and then you have coefficients, which is for batch normalization, so that the addition, the sum of the output does not exceed to the infinity. So you have a lot of like this batch normalization, and these are the coefficients that are multiplied and added, and then you get the output. So here also, from here the weights went, from bottom the inputs went, they all got multiplied, added, and then bias is added to them, and then normalization is done, and then you get the output. So this is the way how you can design accelerator on a chip. How you have to design buffers, you have to design the data router. That's not very difficult. It just routes the data from buffers to the input of the MAC. MAC are multiplier and accumulators. They are just a multiplier, and the outputs are added, multiply accumulator. But And then right, you make the max, you make the weight buffer. Here you keep the memory. You have a DDR RAM, and then you send everything of this, and then this goes, and then you add something to it, and then you get the output. This seems to be simple because each and every circuit here is designed in a simple way. I would show you the coding of Mac. But what's most important thing, you should know the flow, what is going, where is going, at what time the output is leaving the circuit, and at what time the output is coming outwards. So the timing is really important, and the timing is also is configured by software. So I would tell you what is the importance of software over here. But this lecture is for making hardware AI, right? But we will still be having some software on this. So I think everybody got that, how we can have an architecture that implements neural networks for us on ASIC or on FPGA. So what is a hardware software co-design, first thing? So till now what we saw that there are machine learning algorithms, and their hardware, the 4 types of processor we saw that can run machine learning algorithms on them. So we also discussed that we would be discussing how we can design on FPGAs and how we can design on ASICs, but we did not discuss, and we also discussed that how this circuit looks and what are the basic building blocks of the circuit that would be executing a neural network algorithm, right? So what is a hardware software coding? What happens that in 1990s they discussed, and they thought that it would be easier to have a software also work along with the hardware, and that would increase its efficiency. How it would increase its efficiency is example of a smartphone. If you have a smartphone, the phone's hardware, if you suppose disintegrate an old phone, and you will find some chips in it, the chip for an antenna, the chip for a speaker, the chip for the processor, the chip that configures the screen along with the processor, right? So there would be many chips inside your smartphone, and but they would be dead because you don't have anything that makes them on. So there is an operating system that makes the smartphone works. So that operating system is the software for us, right? So whenever we switch on our smartphone, what happens? The operating system loads, and then it says in the firmware, there's a place which boots, right? The operating system boots, and then it orders the smartphone to switch on the power supply to specific places, and then those specific places gets on, then your phone gets on. If your operating system is not there, the phone would not get on. That's why a smartphone is the best example of a hardware software co-design, right? So if we have only hardware, why did it not create any phone that did not have any operating system? The Nokia, the old Nokia, right? I imagine you remember when I was when I was in college, I had a small Nokia phone, right? And that did not have any operating system. It was just a hardware. So what we did when we started the phone, there was the manual button that would on the power, and then it would on the. We need less power, means power efficiency should be more, and then we need a very complex circuit like satellite. Satellite, there would not be a throughput and latency issue. I don't think so. Throughput would be an issue, but power efficiency and area are a very important issue for satellite. At the same time, for Alexa, I don't think so power efficiency would be an issue because it's an ASIC, and area is also like it's sufficient area we have. But we have a constraint on latency and throughput. We need it to be very fast. We need to answer it very fast. Otherwise, we would lose the user experience, right? So for every design, we have different goals. And then what is the precision requirement? You very well know that when you are running your neural network on a simulator on a TensorFlow, you are having the default 32 floating point, this one. But when you do hardware design on 32-bit floating point, the input of the Mac is very big. The multiplier and accumulator that you're designing if you're designing a 64-bit, I think everyone who has done even masters or even understood the VLSI thing, that making an adder of 64-bit and making an adder of 16-bit have an area ratio of around 4:1. Means this would be very small. So it's better to have low precision, but then you would not be having a lot of accuracy. So it's you have to decide that. But presently, present in the present criteria and the state of the art, we are implementing 16-bit because 8-bit becomes too less for accuracy, and 32-bit becomes very big hardware. So better to take 16-bit. It's a good precision. It's a middle place. It's a compromise between hardware and efficiency, right? And what is the workload? And you might be knowing inference versus training, right? What is an inference on a neural network? When we train it, so it's called training, right? How do we train it? When an image and a face recognizer, a face recognizing CNN is given millions of images to train itself to understand the face. It's given firstly. We train it first, that like a human brain. Then when its training is done, it has got its parameters and it's now fixed. Now we run inference. Inference is a testing. Testing means now we run the practical on it. Suppose I have a neural network. I take Oriental Institute of Science and Technology, and I take all the students. Suppose there are 4,000 students. So I train my network on 4,000 students' faces. So that's called training. And then the network is done. And then on a day when it's very important, like on a convocation day, on an event, I'm checking everyone who is this person. So that is inference. That's the practical application. So so our machine learning algorithm, our machine learning hardware can be built for training also, for inference also. Means they would be different. For training on hardware, we would be making different hardware, and for inference also we would be making a different hardware. But training hardware is very big because we take lots of images, millions of images to train a network. So basically training is done by GPUs. Always remember that training, even when we made our own design, so there was a GPU programmer who did training for us, and then he gave us the outputs, the parameters, the final neural network, and now we are implementing the machine learning algorithm on the ASIC and FPGA for inference only. Okay, so training is done mostly by GPU. So, but still there are some ASICs that do training. So that's why they say that workload, we should understand what it is for. Why we are making machine learning algorithm, for inference or for training, right? So we understood the requirements. Then we model, right? So we model the neural network workload. So what is the pattern? Pattern means if we are making CNN, so what is the pattern? We first need input, we first need biases, we need to multiply them. So we need a lot of max in between them. If we are making a random forest, we need for the coefficient, we need a different buffer. If you're using a recurrent neural network, we need somebody who gives, in a recurrent neural network or in Q learning, we have some incentives or some appraisals for the person who wins. So what we are going to use what we are going to use for storing all those data. So that pattern of our machine learning algorithm, we should know what we are going to do and where we are going to store those things we need for. Then we need to know bottlenecks, that how many matrix multiplication we need, and if we need convolution operation or not. If we are having simple deep neural network, we don't need any convolution operations. So we need to know that. And then optimize layers that consume most resources, right? So we would be checking that how we are going to make the layers, how input layer will be there, and then how other layers will be working parallelly together. So this is basically how we design the network on hardware. This is again a pen paper thing. This again has to take place in the mind of the designer who knows how machine learning algorithm works in software, and then he's going to make in the hardware, right? So now the most important thing is hardware architecture design. This is the third step of what we are doing. This we are understanding this flow chart and how we can do how faculties and how researchers here, how we use this, how we make this circuit on the ASIC and FPGA. This is how we are learning. So I did define the requirements. I did model the neural network workload. Now on architecture design. How do we design? So we select the HDL. What is HDL? It's a hardware description language, right? Everyone who belongs to VLSI domain or like even in BTech knows what is an HDL. So basically you can have either VHDL or Verilog, or these days system Verilog is very much into fashion. Why? Because system Verilog has some characteristics like C and C++, like object-oriented programming. Okay, so you can have classes, you can have structures in system Verilog which were not there in Verilog. In Verilog, every statement is a wire or a register or some hardware, right? But in a system Verilog, it's not that. You can have a structure, you can have a table, a task. So system Verilog is really different, but it's really similar to Verilog. Okay, so it depends which language you use, and you can have modeling styles. What is a behavioral modeling? In behavioral modeling, you just tell that you just show if and else, right? If clock's positive edge is there, then add these two. Otherwise, don't add. In structural modeling, you just put into the components, right? If you put some data into adder, you are not defining if else in the structural modeling. You are making some hardware, you are making some half adder, some full adder, and its output you are putting the data. That is structural modeling. You are creating essential structure. In a data flow modeling, you just go using the statements, like you have a wire, say A, and then A has B plus C. So that wire has got B plus C, the sum of two things, and then that wire becomes the input of some circuit. That is data flow modeling, and we have some concurrent statements. Now, mixed modeling is you can use all of them. We actually, in machine learning algorithm design, in machine learning hardware, you cannot stick to any of these three. You need to have mixed modeling. Why? Because the memory design is having a different thing. Memory design is mostly suitable with structural modeling. Sorry, behavioral modeling, because it's like a FSM. Finite state machine when you're designing a memory. But when you're designing a MAC, a multiply accumulator, structural modeling is better than behavioral modeling. Why? Because those constructs are directly mapped on an FPGA. So what you get is basically simpler circuit, and there are less chances of getting latches and all. So it's better to have structural modeling for a combinational circuit, and for memory you have, because it's a sequential one, you need to do a behavioral modeling. So you would end up doing a mixed modeling, right? Now, when we start to build our system, our machine learning hardware, so what we do, we write the HDL code, right? So we use this, and then we use that language to describe the behavior of each block. And the most important thing is in any of the languages, in VHDL and Verilog, there is a set of synthesizable constructs. There are also some constructs which are not synthesizable. If you say that, if I give you an example of a synthesizable construct, is a while loop. A while loop in Verilog is not synthesizable in many cases. So if you code using while loop and you go for synthesis, that logic is not going to be put on the chip by the tool. The tool is not going to do that because that construct is not synthesizable. So if you're learning any language, if you're coding in any language, you must learn it thoroughly, and you must know that which of the constructs that I'm using are synthesizable, and that would result in an actual circuit being formed on that chip, right? And then you can use any of the top-down approach. Means, what is top-down approach? Like you first make the entire plan, and then you start with making memories, and then you make smaller architectures, and then you join them using wires. That's also based on coding, right? You first make suppose a full module, right? You know how modules are made? I will explain you this top-down, bottom-up approach with the next slide. So this, firstly, I'll explain you what is the code for a multiplier and accumulator. You see it's in Verilog. So it's a simple one. If you want to model a Mac, I just told you that CNNs use a lot of Macs. So in a Mac, you just do multiplication and addition. So you just input, this is a 16-bit Mac, right? So it has inputs clock, reset, and then an input A, B, and then an output, and then input again. This one, this input is what you're going to add. This is not the product, the output. This is what you're going to add to the product. Now this is the output, Mac out, and then this is the product. This is the product of A and B. So how you are going to write it? Always add posage clock and posage reset or posage reset. Why we are doing this? Because some of the part of machine learning algorithm need not to be synchronized. So if there is no positive edge of the clock, you can also do this operation on positive reset. Why? Because I just told you in one clock also there are many operations performed. We have one of our project in which in one clock we have like 17 to 18 operations performed in one clock. So if you just always put posage clock, so it would only perform at the clock's edge. So if you don't want clock's edge, you can keep another reset that it would perform this operation at any of these, positive edge of the clock or on the reset. If reset, begin. Mac, if there is a reset, means you don't need anything output, right? Any output. So Mac's output would be 0. 32-bit 0 means 32, in a 32-bit representation, the output would be 0. B means binary. In binary, 32-bit number and its output should be 0. So when there is reset, we get the output 0. But if there is no reset, the product is A into B. You multiply it. Now this multiplication is performed by the chip, by the FPGA when the tool sees this, right? Even if not FPGA, if ASIC. Anytime when the tool is doing that for you, the tool sees your design and the tool is synthesizing this into hardware for you. This is your code. So what does the tool do? It sees this multiplication and makes a multiplier by itself. And how does it make it? It knows that this is 16-bit A, this is 16-bit B, so it makes a multiplier, multiplies both, which can multiply these two. And what does Mac out do? The tool also make a Mac out output, which is an adder. So it knows that the product is 31-bit, right? So the adder should also be 31-bit, and you have given the product output also. So the tool is making that for you. So this is how your designing would be resulted into a hardware by the tool that's making. What is a tool? For ASIC, we have different tools. For FPGA, we have different tools. I would give the name of all of the tools in the last, right? So this is how you enter a Mac design in the tool, right? What is a tool like? It's like you people might be knowing Xilinx ISC, Xilinx Vivado, right? So these are the tools which make your hardware for this, which are used for making hardware. So in those tools, on an editor, like on Synopsys, we have a design compiler. So in design compiler, there is an editor. We write this, and it would be converted to circuit, right? So now which step is this? We are where? We are here. So we define the requirements. We have done architecture design. How we have done architecture design? We selected the language, and we started coding. We coded Mac, right? We just saw its code. Similar to Mac, we coded other memories. We coded the buffers. There are simple codes available everywhere. Even on ChatGPT, you can ask for the codes of these things. But the most important thing, you should know how you are going to integrate all that to produce a machine learning algorithm, right? So the code is not an issue, and code you would get these days very easily. So you would be having all the code, and you would be putting it on the editor of Synopsys design compiler if you are in ASIC, or on the editor of an FPGA of a Xilinx Vivado if you are an FPGA, if you're working on FPGA. So you're going to put that in the editor. Now you're going to do simulation. How? Now you have to connect that code, right? How you're going to connect that code? You have connected all the memories together, and then you should know that the memory is connected to then multiply max, and then max are will give the output together, and then it would give the output finally. So you have made such design, but you have not yet made the software. So I'm not talking about software right now, but you have made entirely the you have integrated all of these circuits together, so that when you do simulation, so in the simulation you would be throwing the inputs to get the outputs, right? So you have a circuit. So how you are going to test it? You throw some inputs to the buffer, right? You have made the buffer. You remember that we had initially we had this buffer, or you can say this one. This was a buffer. You have made it on using HDL on the chip. You have made these P arrays have MAC. These P arrays means MAC, right? This is what these are. These are calculation units, right? So this is PEs. So in these they have MAC, or you can see this one. So you are putting, you have buffers, you have designed everything on using an HDL, and now you want to simulate. How you would simulate each of these entries? You would put in a test bench. Test bench is also a code of Verilog or VHDL, whichever language you're using. So you would just put inputs. You would be having some inputs, and you will give them some values. For example, I would give one input. What are buffers containing? Buffers are containing image pixels, right? So suppose I have an image and I have kept its pixels. I did that using software. We all know image processing, right? So we can get image pixels using any of the Python tools. So I've got like 9 images, some pixel, one image. So I just put into the buffer. So what would we are doing? I would be using test bench. I would be giving those all inputs here, and then weights I would be giving through another input. That would be done again by my test bench. Now those weights and buffer inputs will be multiplied, and they would give me some output, and that output I'm going to get in this simulation as the output, right? And if those outputs are correct, because I told you that we need to perform this we need to perform this all in the software also to check the design of a machine learning algorithm. So we have the outputs also for that. We have in our software, right? Okay, so we know the outputs. So when we use simulation, we get the outputs of the thing that we want to simulate, that we want to run. So simulation is a testing, right? If it's wrong, if it's not coming, most of the time after designing, it's like the language designing is done in 1 month mostly. In 1 month you design everything, right? In 1 day you design a Mac, in 1 day you design memory for integration, for everything. You don't take more than a month. But most of the time is lapsed in function simulation. When you give your inputs and you're not getting correct output. Why? Because you wrongly coded some Mac, you did not do correct coding for memory, and it's some timing issue. Timing issue will come later on. But functional simulation will give you, if your output is coming correct, you should be happy halfway. Means you have done most of your work and you are getting correct output in simulation. Now what you need to do, the hardware stuff, because there will be a lot of stuff left. But if you get correct outputs, your half of the work is done. And mostly the researchers, I think in the master's degree, when you are doing MTech, and many researchers and PhD students who produce some papers, they just go to simulation. And some of them also go to implement that thing on FPGA or ASIC. But as I've seen, that even if you go to simulation, you produce your results. If the journal or the conference is accepting that, it's well and good, right? So simulation for ASIC is done using Model Sim or QuestaSim, and FPGA use Vivado integrated development environment. What is an integrated development environment? Vivado has Xilinx ISC, Xilinx AMD is the company that produces massive number of very good functionality FPGAs. So they have provided an environment to do everything which is mentioned in that blog design on the Vivado tool, right? So that they have given you the simulator, that's XIM. You can simulate it. You just press one button, all of that, and you just make a good test bench, right? You just give inputs and outputs, and when you get the simulation waveform, so you have verified that your design is working correctly. Okay, so you have to test bench, right? The most important skill over here is a test bench. Now so what are the important things? Yeah, these are the things I've already discussed with you that we should be, the important things that we need to take care of is Mac, the correct Mac designing. We can also use systolic arrays. Systolic arrays are very famous design for machine learning. Means consecutive elements of the arrays are there which do your multiplication for you, and then you can choose an optimal data flow pattern. You understand how data pattern means, how input and output are going. Some people make FSM also, finite state machine, to design the flow of input output through the machine learning algorithm. So you can see that how FSMs are designed for making ML algorithm hardware. And then you can understand which memory you're creating. You should be very focused upon that, because SRAM and DRAM, they all have their own problems, and they all have their issues, several advantages and disadvantages with respect to some energy efficiency and the speed. Right? You can select for interconnects, especially in case of Vivado. You can select those, and then you can also make a scalable. Means you can if you want to have a scalable design, you want to make it a bigger neural network on the same chip. You need to consider a lot of issues before that. If you want to scale up your design, right? So now hardware design optimization. If you want to reduce the precision, you can give only 8-bit inputs, right? And then you can it's like you can make a smaller multiplier, and then you can exploit parallelism. There are various books of Verilog and VHDL that explain how to achieve parallelism in data, how to achieve parallelism in task when you are implementing. So you can learn all of that. That's very good and very important for that if you are learning data parallelism, because all the machine learning algorithms work on parallel data. So there's a specific way to design your circuit. There is even in Mac, you have a number of ways you can design a Mac, even number of days you can design a machine learning a hardware structure to make it more parallel, right? So now energy efficiency means you can gate your clock. We all know gating our clocks, right? So it would increase our performance. We can do voltage scaling. We can do efficient power management, and then we can use custom for ReLU and cooling and softmax. These are what? These are neural network functions what activation functions. What do? They don't let our output go exponentially high, so they just limit our output. So we can have different structures for ReLU also. Like we don't want just multiply, so just make a small circuit for implementing ReLU. So it depends on us how we are designing this architecture. It depends solely on the designer, and then how configure all the elements, all the blocks of it. How do they together work? Now in simulation prototyping, yeah, you can just go for cycle to cycle simulation, as I just told you, behavioral simulation. And then for FPGAs, you can test. If you're going for ASIC, you can test on FPGA. That's confirmed. And then if you're doing ASIC implementation, you have several more things. You have, as I told you, there was a big block which could be done by backend designer, but there are a few of them I have written here. Write register transfer language, right? You can write RTL. You do place and route for yourself. You do verification, okay? And then what is a tape out? A tape out is something that you send to the foundry for making your ASIC. Right? What is tape out? It's done by after everything. This block I just told you. So after all of these things are done, then there's what the last product is, tape out. So that you send to the foundry, they make the chip for you. Okay. Post silicon validation, when you are foundry. So there are three foundries that are more famous in the world. But these are the ones, these two are ones you send, right? Any send their circuits TSM. So here, even IIT Madras, I have listened. So there are some foundries even in Madras. So they create the chips for you. There are local startups that make chips for you. I don't think that they would be that local, because ASML is a company that provides those laser and all the devices that makes semiconductor silicon work, right? So the local startup would not also be not very small, but still there would be foundries everywhere, like in New Delhi, in here in the UK. We have a small foundry which is called small foundry. So they just make, like, in very very less charge they take, and they make our chip. So you have to find those chips, and if you are associated with some IIT, or if you are working alone as a researcher, so you need to have a look on which foundry is going to make it that for you at the cheapest price, right? So after testing all, you're going to send it, and foundries also check the design specification, right? They provide that for you, and you can analyze and optimize performance and thermal characteristics. Everything means if it's going to work on satellite, so it would be having such and such temperature, so it should be suitable for those applications. So everything it needs to be tested on. This is a problem with ASIC, but not with FPGAs, right? What do you do on FPGA? As I told you that when you are making on FPGA, simply do synthesis, and then you press the button of implementation. The netlist would be put on the FPGA, right? FPGA, as I told you in the beginning, that it's a chip, it's a big board on which there's a lot of space for programming. So when you program, that program is put on the chip, and then those when you do simulation and when you run that program, it works on that. So on FPGA you don't need to do anything. So FPGA is really good for researchers. When you just put on your design on FPGA, it does implementation, it does placement, routing, and floor planning for you. Same tool is doing everything. You don't need any of the back-end designer. You just design till here. Now the rest of the work will be done by FPGA via the tool. All of these things, right? So you get your outputs, and after functional simulation, right? You have done everything. Now here you need to verify one more thing, that on the chip, on the FPGA, how does the hardware runs, right? So on the FPGA, how does the hardware runs? We need an integrated logic analyzer. I didn't mention this in this PPT, but this is important, that integrated logic analyzer is a software which you put in your design, which you call, it's a module which you call in Vivado. So, and you send the inputs you want to monitor. So it would give you a waveform while running FPGA. So in real time, when your algorithm is running on the FPGA, you can monitor here on using an integrated logic analyzer ILA, right? So you have done the functional simulation here that your circuit is working, and here you would see that your hardware is also working. Now I would later come to software integration, just in 5 minutes. So how did you test your FPGA using ILA, and how did you test your ASIC? You have sent it to the foundry, and you have got it meet the design specification. You saw that it performed well, and the foundry also validated that it performed correctly. And then now, what is software integration? Okay, as I told you earlier also, that our smartphone is nothing without the operating system. So we make two things. We make a software to run on the machine learning hardware, and machine learning hardware is at its place. So there are two components of our machine learning accelerator. The first component is the hardware that we have designed using HDL, which is working on the chip, which we have simulated, which we have tested. Now we need a software. Why do we need a software? So those are called drivers, compilers, and firmware for communication with the host system. What is the host system that we have designed? We have designed a processor that performs our neural network algorithm, right? So there will be a compiler. You remember how does a driver works? A driver works by switching on the things and letting the things happen, right? So how do we work actually with the drivers? Okay, I would tell you that. I think I put that later. Yeah. So I would tell you software tools first, right? So I have Blender for ASIC. In a Blender, this Blender is used in ETH Zurich in Switzerland. So how do they do? Blender is a tool. They have in that Blender they have so many tools together. They have a mental graphics simulator there. They have they have a cadence system designer over there, a synthesizer over there, and in the same they have a C++ compiler also. That C++ compiler and all the hardware design tools are inside one tool called the Bender. And then when we start the Bender and we run the application, the C++ code says to the ASIC that switch on the power, and then its power switches on. So it's an operating system. The C++ driver, it becomes an operating system on the hardware, right? Similarly, for FPGAs, we have Vitis. Vitis is also free like Vivado. When you are downloading today, if you install Vivado, Xilinx Vivado, you install, you can just click and have Vitis also along with it, right? So when you have Vitis, what you do when you design in Vivado and you have made your simulation done and you have your implementation done and your static timing analysis is for completed properly, then you go to the left and you go for export system design. The entire design and netlist is exported to a file and kept anywhere. When you open Vitis, you take that file. You import that file in Vitis, and then Vitis you just make a C code which is very simple, and a lot of help is given on internet and on the Vitis documentation. You create a small driver that would run the algorithm. You don't need to specify which machine learning algorithm. You just need a driver that runs on your hardware. So this is for software on FPGA, right? What we do here in our university, what we do, we have a different approach, right? So what we do is, I didn't explain you this thing, right? The tools for the hardware. Yeah, software I told you how do I integrate, but tools for hardware I didn't tell you. So if you're designing ASIC, you have Cadence, Synopsys, Siemens. Now these they have their own pros and cons. I will tell you in the next slide. But for FPGA, if you're designing an FPGA, I recommend everybody who attended this workshop or whatever the lecture, so they can install Xilinx Vivado free of cost, and then it's completely free until you go for a lot of power analysis and lot of static timing analysis issues. If you need a licensed one, otherwise you can work. If researchers can easily work on Vivado and Vitis, and then if you have an Intel FPGA, you need Intel's Quartus Prime, right? So these are the tools, and as far as ASIC is concerned, the tools have some advantages over one another. So what I worked on Synopsys, so these are very, very costly ones. So they need to be provided you by the institute, right, or any organization for which you're working. So they are very high cost, and they are very, very encrypted. You cannot means you have to do a lot to switch to just open one tool and then work on it, and they're so difficult. The data is not found anywhere. So you need to be very, very having a lot of a lot of training in all these also is required to work on it. But I wouldn't demotivate you, because if you will, you can create the way. So, but still there would be for this is front end simulation, right? The first simulation. So VCS is used by Synopsys, and Siemens use Questa. And for synthesis, we use design compiler. What is synthesis? That I wrote my math module, I wrote my machine learning code, and then I have to convert it into a chip, right? I have to convert it into hardware. So that would be done. That's for synthesis, synthesizing your code to a hardware. So that's done by design compiler of Synopsys, right? About its place and route would be done by IC compiler, and then time analysis, prime time. So you would say, oh, how we are going to use so many tools? No, they all are integrated mostly, right? They have told in this that they all are different, but there would be one environment in which you can be doing this all, right? But for good organizations, like you're working for a semiconductor company, you are working for some ASIC design company, so they buy these all licensed ones. They are different ones, and different engineers would be working. Some of them would be working here, some of them would be working here. So this way, I told you that each other. But otherwise, as a researcher, they all are integrated also, and you can work on them. So this was about ASIC tools, right? And FPGA, as I've told you, that FPGA tool is Vitis and Vivado, and the Vitis is for software, for hardware software code design, and Vivado is for hardware, right? So these are also frameworks. These frameworks help you to make direct hardware. Means if you code in C, or if you code in Python, you get hardware, right? But as I told you, they're not really efficient. Efficient ones are you, which you make yourself. So, what are the useful things you can do for now? What is the key takeaway of this lecture is, I believe that what I've told you, that it's not very difficult to make a machine learning algorithm work on your own chip, right? So a very good lecture is Vipin Kizibat. He is a professor at BIX Pilani, India. So he told A to Z everything, how you can model a neural network on an FPGA. This was very important for me. I've learned a lot from this one, so I want to share with all of you. And for various design that for researchers, there are around hundreds of FPGA, other hundreds of machine learning accelerated designs shown in this survey. Okay, so this is a review, and I hope if you see this, you would really get a lot of knowledge on what can be the architectures, what can be the memories for different ML algorithms, what I can do, what can be useful for my research. And I hope you understood. And if you have any doubts, you can ask me. Thank you. Am I audible?
Yeah, yeah.
Yeah, am I audible?
Yes, ma'am. Hello, am I audible?
Yeah, hello. I can you
Yeah,
can
yeah.
you, can you hear me?
Thank you so much,
Yeah,
ma'am.
yeah,
Actually, I have one query. Once we start the
yeah.
using the ML algorithm on the VLSI design, so increasing the complexity of routing and the complexity of because of the complexity of this ML algorithm, the hardware requirement will also increase.
Yeah.
Am I right? So
Yes.
power dissipation
Yes, 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 of
will
course.
be effect. So is there any is it also the part of the research that we can work on to reduce the routing complexity to improve the efficiency?
Yes, of course. Routing complexity is like here also. If you make a larger design, you can opt for the floor planning concept in Vivado. Xilinx Vivado, you know. So if you run Vivado, you have one way in which you can do your own floor planning. Did you get my point? When there is a routing complexity, what do you get? You get. Are you talking about power dissipation?
Yes, yes, yes. The power dissipation and the
Yes, yes. So
will also.
yeah, when we have a lot of routing complexity, we can do our own floor planning. We can reduce that with floor planning.
Okay, okay. Yes, ma'am.
You can change the locations of the things, right? You can change the location of block RAMs if you are using block RAMs in FPGA, or if you are using memory. Wherever you are having that routing complexity, you can change its location and try various places, so you can have.
Yes, ma'am. Yes. Hello. Yes, ma'am. Yes, ma'am. Yes, ma'am. Got it. Uh, Thank you so much, ma'am. Actually, that session is much more related
Any other queries?
experiment level and which is very helpful for the researchers, ma'am, because this
Yeah.
is related to real time
Yeah.
implementation.
Yeah. Anybody can mail me if they have their personal queries regarding this. I'm happy to help. And we are designing machine learning accelerators. So we are just two people in our group. One is for software, and I'm for the hardware. So we are designing on FPGAs. So somebody who matches, who want to design on FPGAs. I know ASIC also, but if you have any queries regarding FPGAs, I would be happy to help.
Sure,
Okay.
ma'am. Sure. I'll circulate the email ID on the FDP WhatsApp group, and whenever they wants to
Yeah.
connect to, they will do by the mail.
Yeah.
Okay.
All right.
बेटा
Thank you
इधर
very
रोक
much.
रोक रोक जल्दी रोक थोड़ी दूर. So thank you so much, ma'am.
I'm sorry. The voice is
Hello. So thank you so
problem.
much, ma'am. It
Yeah,
was
yeah.
a great pleasure to
Yeah. Thank
have
you
you
so
here
much.
as
Thank
an
you.
expert, ma'am, and that will be very helpful.
Even for me also.
Thank you so much, ma'am. Thank
Yeah,
you.
I hope so. And for me also, very good experience again. Thank you so much. Thank you.
Thank you. So I am ending the meeting. Thank you so much, ma'am.